Hello, welcome. So in this series, I am building a FPGA stack machine CPU from scratch. Um, what that means is I'm building it in digital, but I'll export to Verilog, which is possible. Verilog is what would run on an FPGA. So I may try to get into how all of that works in the future. But first, I kind of like to get something working. So in the previous episode, I've been working on the stack here. There's a ability to push things onto the stack. So if we do this, then it'll update the top of stack, and then we can push from there. So let's increment this. And then if we increment this again, we see that we're pushing onto there. Now you can't see the value here because this is high, but if it goes low, then you see that we've got our three values here. I can push a couple more on there. Okay, so we've got those. And if we look in the stack memory, we can see that we've got our values in there. Yep, and we should be able to pop those off. So if we do pop instead, then you should see 2D go into the top of stack, and then 2B will become the bottom of stack here, or the third on stack. And that is working. And yeah, so that's what we've created last time. Let's see what we should do this time. I think getting some numbers being added would be useful. That's usually where I start. I wanted to start there last episode, but got distracted by building a stack instead. So let's do that. Let's see. I think it makes sense to move all of this into a separate circuit. And I guess that means the clock needs to become an input here. So if I'm in presentation mode, then tooltips don't appear, which is nice because the tooltips kind of mess with YouTube compression and all of that. But then I can't see the grid markers. And if I turn that off, then every time I hover over something, then you get a big help text. And that is really annoying. I guess I just accept that there won't be grid markers, I suppose. Okay, let's see. This needs to be a separate embedded circuit, I guess. This one is not in presentation mode. Okay, well, whatever. So let's just copy all of this. And my usual circuit settings here. Okay, so we got so much free space now. Um, let's just verify everything works. It seems to. Um, yeah, okay. So what do we do next? I want to hook up basically a proxy for an ALU onto the first two lines here. So let's do that. Okay. Um, I reversed the order of the pins on this side because the top of stack is actually the B input into the ALU, and the next on stack is the A input. Because if you think about it, if you push a immediate value on the top of the stack, you want that on the right hand side. There's a few operations where that actually matters, but that's generally what you would want is the top of stack to be your immediate that you just pushed on there, and then the next on stack would be the A input into the ALU. Now, in the case of adding, it doesn't matter. You can swap the inputs, no problem. But if you're, for example, shifting, you would want the immediate to be the shift amount, right? So in that case, the B input would be the shift amount, and that would be the top of stack. Similarly, if you're subtracting, you would want to subtract the immediate, and that would be the top of stack, right? So that's the way to think of that. And it kind of gets the other pins out of the way because these are just for debugging. These ones up here, the third on stack and the stack pointer for now are just for debugging. So this should work if we push things on there. We can put our usual 42. I've got a purring kitty on my lap now. So you might hear her, you might not. I don't know. It's hard to say what the noise suppression will tune out. Okay, don't rub yourself on the mic. Okay, well, you're definitely going to hear that. No, don't eat the mic either. Okay, if you're going to destroy things, you got to go. Okay? You got to behave yourself. Do you want to stay? Oh, goodness. Kitties. Okay. All right. Now I'm thoroughly distracted. Okay. So we are adding numbers and we've got 55 out. So now we need some way to put that back on the stack rather than inputting a number here. So, yeah, let me think about that. Okay, let's see. We have 42 here, and we want to write it. So that, and then if we push and we increment this, yeah, and then if we disable this and we pop, I guess? No, no, that didn't work. We need a separate control signal for this, I think, because I wanted to push this onto the stack. So that didn't work. Okay, let's try this again. We push, let's just use a small number. We push 1 onto the stack. Well, we first write it to the stack. We might as well push. Sure. So we do that. We have, what did that do? It pushed 0. So we need mux to be 1. I think actually that should be the other way around. I'll fix it after. Okay, so we do this. Okay, now we've got 1 on the top of stack. We do 2 here. Cycle the clock, and we've got 1 and 2. 1 and 2 is 3. So if we do this, we don't want to push, we want to pop. That didn't work. Why didn't that work? Maybe it was premature and pulling the stack out, because we want to be able to update the top of stack without, yeah, why didn't that work? Let's go in here. So we want to update the top of stack from the input. The input will be 3, and we want to pop at the same time. Here we go. This is what happened. So it popped from NOS, and that's not what we want. So we almost need to make this mux bigger. Okay, took me a little bit to figure this out. Originally, I tried 4-position mux, which would work. I just thought breaking it out into separate control signals would be a lot easier to remember. Okay, is 0 this, or is it 1 0 this? So this is what's called one-shot encoding, where one is high and the others are, like, if you make more than one of these high at the same time, that's undefined behavior. We can make sure that these are mutually exclusive in the microcode once we get that far. But for now, this is easier. So let's just do it that way. If the write enable from I to toss is high, then it turns on this mux, which sends the value of I through into toss and turns on the write enable. If we have NOS to toss, then it sends the NOS value to toss. If we have Y to toss, then it sends the Y value, which it does by default. So it doesn't need to change a mux to do that. So those are our 3 options, and I think this is wired correctly. Let's test it in the upper circuit here. And we need to change the order of the inputs here. Okay, let's see. 1, and we want to write from I to toss. I clock it, that worked. 2, and we want to push this one. Okay, so far so good. Now we want to go from Y to toss, and we want to pop. That worked. We've got 3 in toss. That's what we want. Excellent. Excellent. This is working quite well. Okay, what to do next? I kind of feel like some way of making a program to sequence things would be a good next step. Let's see. Okay, let's try this. I created a bit of an assembler here that allows me to figure out what these hex codes are. I had it wired up and then I was like, hey, wait a second. How do you even know what this hex code does? So I put a bit of a program display here, kind of a debugger that shows you what it's doing. So the first one is hex 24. But what does that do? Well, it's sending I to the top of stack, and I is 1. So if I cycle the clock, then the next instruction is to push I to top of stack, the number 2. So that should put 1 in NOS and 2 in TOS, and it does. And then I pop and put the result of Y in TOS, on the top of the stack here. And so that should pop 1 and 2 and then push 3. So then the only thing on the stack should be 3 at that point. And that's correct. And now I'm pushing I to TOS with the number 4. So that should put 3 in NOS and 4 in TOS. And it does. And then we've got 7, and that's going to be popping, and then Y will go into TOS. So then 7 should be the only thing left on there, and that's the case. Okay, so we got a bit of a program going here. It's kind of tedious to change the program in that I need to use this and then stop the machine and then start it again. So, I wonder if there's a way that could be fixed. There is a component that can save between runs. I believe it is called an EEPROM, and you'd want the one with the separated ports, I think. Let's see. The nice thing is you can see the program here, but then again, these hex codes don't mean anything. So, but I might want to keep these so I know what to enter. Well, wait. No, I'd have to enter the whole program again anyway. Well, I could enter it directly into the EEPROM. Okay, so let's do this. Okay, so in theory, if I clock it now, it should store it between runs. So let's just test that before I enter in the whole program. So it's in there. It's the correct value. Let's stop, then start again. And it's still in there. Awesome. Okay. So we've got a way to program the program memory here. So I'm just going to skip ahead to the second spot, and then we want to store, and we push I to S2, and that's 45. It's kind of small, but you can trust me. And then we push. No, we pop Y to TOS, and this should be 0. and then clock it in. And then we put 4 on the top of stack. We push it. And then again, we zero this out and put Y to top of stack, and we pop. Okay, now the program should run. So we're putting I to the top of stack. I is 1 here. And then we push 2 onto the top of the stack, which happens. Excellent. And then we take Y and we pop it off, and we get 3 in the top of the stack, and then we push on 4, and 4 is pushed on there, and then we pop 7 and put it in the top of stack. And that's exactly what happens. Excellent. Yeah. So we have a way of assembling a program, and we can do custom ASM soon on that. We've got program memory, a program counter. We've got a way to display what the machine is going to do. And we have our stack. And we've got an ALU, which I could probably call this ALU. Let's put it in air quotes here. So we've got just an adder acting as our ALU for now. So that's why I put it in quotes. And we don't need these because we've got the program in the EEPROM here. So I think that is a wrap. So what do we call this episode? Let's call it program. I don't know. What do we call this? Okay. Yeah, I think this is a good title for this episode. We are running our first program. Yay. So, yeah, I think this is a good place to end it for this episode. The usual blah, blah, blah. There's links in the description, both to this program. So this program is Digital by H. Neiman. You can find it on his GitHub. If you search H. Neiman and Digital, you'll find the GitHub link, but it's also in the description down below. There is a link to the GitHub repo with a commit for this episode. Just go through the commit history and you'll find the episode in there. So then you can take this at the current state in this episode, and you can play around with it and see how it works. I highly encourage you to do that because it helps with learning if you are indeed learning. And then you can kind of play around with making different programs at the current state and tear it apart, see how it works. So yeah. Thank you very much for watching. If you're feeling generous, there are links in the description for that as well. But otherwise, whatever you want to do is what you want to do. It's very much appreciated. So yeah, have yourself a great day. Bye.